In this video, I will go over some of the basics of probability theory. I'll approach probability from both a frequentist as well as a Bayesian point of view. Most importantly, I will end this video with the statement of Bayes' theorem. And this particular theorem plays an important role all throughout this course. Now, there's many things to be said about probability theory, and I think this is one of the most important statements to be made. It's taken from the book of Bishop, where he says basically probability theory provides a consistent framework for the quantification and manipulation of uncertainty. So this uncertainty aspect plays a central role all throughout this course and plays a central role in machine learning in general. And so in this machine learning context, we have to deal with uncertainty in various ways. First of all, we have to deal with uncertainty on my measurements, because there's noise on measurements. I have to make observations. We always are interested in some real world phenomenon, and we want to recover it, we want to model it. But we almost never have exact or direct observations. There's always some measurement noise associated with it. And sometimes we know what this noise is, sometimes we don't know, but we have to take into account there's some noise on the measurements. Now, there's also this notion of uncertainty related with the finite size of data sets. You can imagine that that if you have a smaller data set, well, then you know less about the underlying structure or the underlying distribution of the data set. And really only when you may have seen everything in the world, everything in the universe, then maybe with some certainty you can make very strong statements about what this data represents. But in reality, you always have to deal with a finite data set. The example that we saw before, for example, related to overfitting, this is really exposing this notion of uncertainty related to the finite size of my data set, which basically sort of tells us that close to my data points, I'm actually doing a good job with fitting or describing this real world phenomenon. But outside of this, when I encounter new data points which I haven't seen before, I'm going to make a lot of errors typically. So so that's it about finite size data sets. Now, when we talk about probability theory, we can take on a frequentist interpretation, in which case probability is defined as the fraction of times an event occurs in an experiment. So in this setting, we're going to observe random variables, and we just count how many times a particular event happens, and then this defines a probability which we use to make predictions for the future. In a Bayesian approach, the viewpoint is fundamentally different. In this case, probability takes on a meaning as a quantification of plausibility or the strength of a belief. And in a way, this is a more modeling-based approach. It's a bit more generic, and let's just go through an example. Suppose I flip a coin and it lands heads or tails. And I observe, so now I take on the frequentist interpretation, I observe that it lands 5 out of 5 times it lands on heads. So that tells me, well, the probability of this coin landing on head is 1, always. It will never land on 0. Now, in a Bayesian approach, you are actually able to assign also probabilities to events that never happened before. For example, so this is a bit more modeling approach. So you start off with the prior belief that my coin is fair and it lands equally often on heads and tails. So my prior belief is that the probability of landing on heads is 50%. But then I start making these observations and I see it lands more often on heads. Then I can adjust my model. But still I do not fully discard the idea that my coin cannot fall on tail. So I will go over some examples later on, but especially this Bayesian approach plays a very central role in this course. And if you go to the book of Bishop, you will notice that, it takes a very heavy, Bayesian viewpoint on machine learning. And, this is nice because it provides a way of dealing with uncertainty, also relating to events that you have never encountered before. Okay, so then let's actually start about talking about probabilities. When we talk about probabilities, we're dealing with random variables. These are stochastic variables sampled from a set of possible outcomes, which means that every time I make an observation of such an X, it takes on one of the values in this set of possible values x. So all possible values are indicated with capital X. This indicates the random variable, and one particular observation we denote it typically with a small x. Now this variable can be discrete, it can be continuous, and it always comes with a probability distribution, which assigns probabilities to a particular event x happening. And this probability is always equal or larger than 0 for all x in my possible set of outcomes. Again here, so we have P of capital X that denotes the entire distribution on the random variable, and P of small x denotes the probability of one particular event happening. Let's go over some examples. When we talk about throwing a dice, it can take on 6 values. So 1, 2, up to 6. So that's my capital X. And the probability of one of these values happening, well, considering it's a fair coin, this probability of for each x is actually 1 over 6. For each x, so for each x in this set of x values. Well, the same for flipping a coin. Now the coin can take on two values, heads or tails, and the probability for x landing on head is a half, and the probability of x landing on tail is also a half. Right, so okay, so we have a set of possible outcomes, which indicates my random variable x, and then I have probabilities assigned to each particular event happening. Okay, now let's go back to this frequentist interpretation of probability and consider the case of two random variables. We have a variable x, which in this case can take on the values x1 up to x5, and a random variable y, which can take on the values y1, y2, y3. And now we're going to define the probabilities of these events happening by making observations. So we have this random variable and we make n trials, n observations in which we sample the values for these x. And we start counting how often I encounter a particular combination, and we call this nyj. So nyj is the number of times that I observe xy together with yj. And this then defines my probability for future observations of this event x taken on the value xy and y taken on the value yj is given by nyj divided by the total n, right? Because it's a fraction of times that I observe something. Similarly, if I'm only interested in the xi variable, then I take a look, so if I'm only interested in observing the xy variable, then I take a look at all possible outcomes, all possible observation in which I see xy happening with a particular yj, xy, particular yj. So I sum over all these, I make a count of every time I encounter a particular xy with some other yj, and I don't care about the yj. So this count is given by the total sum in this column, and it's defined over here, right? So we call it a marginalization. We move this, we sum, and we move this sum to the marginal. Okay, so again, in this frequentist case, I count how often did I see xy. Well, that is given by cy divided by the total number of observations that I made. Okay, so now I have a probability defined for, well, this joint probability of x and y taken on particular values together, and I have a probability of just x taken on some value. With this, I can actually establish an important identity related to probabilities. So let's just rewrite first this term, so I mark it with a star. and write nyj in terms of the probability. So nyj is the probability of x taking on the value xy, y taking on the value yj, times n. Right? Because n, yeah, okay, so this gives us the number of times I made this observation, and I made n observations in total. Then what I'm going to do, I'm going to use this marginal equation over here. And I'm going to insert this expression for nyj in here. And we have this equation, this identity, and I put it in on the left-hand side. So here I'm going to plug in this probability definition for the single variable xy. And what we then get is that we have that the probability of x taken on the value xy is given by the sum over these y values of this nyj. So let's write it out. X taken on xy, y taken on yj. And these n terms, they cancel out so these cancel out on the left and right hand side. So what we just have derived is called the sum rule of probability. So it says that the probability of, well, x taken on some value is the marginalization of the joint probability over the y variable. So this is called the sum rule of probability. Yes, so what we did here, we made a definition of these probabilities, and then we rewrote it based on this counting intuition, and we came up with an identity that is always satisfied. Okay, now what we're going to do next is derive a second identity, but first we're going to define a so-called conditional probability of y occurring given the fact that we already observed a particular value of x. So again, we have two random variables, x and y, and now suppose I already have observed my x value, then I'm only considering the options falling in this particular column. And again, in this frequentist interpretation, I will look at a fraction of times that this particular event occurs relative to my total number of observations that fall in this category. So the conditional probability of y taken on some value yj, given that I already had made an observation xy, is then given by nyj divided by cy. Right? I make an observation of y taken on some particular value, given the fact that I already have observed some xy. So I'm only considering these cases, the sum, the total observations, where xy took on some value was given by cy. Right? So this is a definition of the conditional probability of y given x, specifically in this frequentist interpretation. Okay, so now we're going to do something similar that we just did before, and we're going to rewrite nyj in terms of this probability. So nyj, the number of times this particular event happened, is given by the probability of yj given that I observed x y times cy, right? Because this comes from this identity divided by n. So I'm rewriting this term over here. And then we also know that the probability of just making the observation xy is given by ci over n. So let's insert this also in the equation. So that gives me that that tells us that the joint distribution of x and y is given by the product of this conditional distribution of y given x times the probability of x taken on this value xy. And this is called the product rule. Okay, so we have derived another important identity. So in addition to a sum rule, which talks about marginalization, we also have a product rule, which basically says that I can always recover my joint probability distribution from the conditional distribution multiplied with what we call a prior distribution, which is only dependent on one of these variables. Now let's take a look at some examples visually. So again, we have two random variables, x and y, and we're going to make observations. And this defines then a data set of observations, where every time I observe a particular x and a particular y, and I have 60 of these observations. So this is an example from the Book of Bishop. And now I'm going to count how often this each observation falls in a particular bin. So that's what we see. Well, and that's what we saw in the previous example. So with all these observations, we're going to build, or we are able to build a joint distribution. If we're only interested in, let's say, the x variable, we can marginalize. So we can marginalize in this direction and observe this marginal distribution px. And the marginalization is taken over y. So you could say we marginalize over y to obtain the marginal distribution p of x. And we did this via the sum rule of probabilities. Similarly, we can marginalize over x. So we're no longer interested in x. We only want to know how often did we see y happening, or what is the probability of y. So this gives us the marginal p of y. And again, we use the sum rule. So we marginalized out all these x values of this joint distribution. Yeah, I'm going to write it like this. Okay, so that gives me the marginal py. And finally, we can take a look at conditional distributions. So given we have already observed y is 1, what is then the probability of an event x happening? So in that case, we're only looking in this particular block, and this gives us the conditional probability distribution of p y given x. Now for each of these distributions we have that we have this normalization property, meaning that if we take the sum over the particular random variable, let's look at the conditional probability distribution, the sum of y taken on the value yj given xy equals 1, right? The total, suppose I consider everything, then this probability is 1. And in the case of the conditional probability distribution, this actually directly follows from its definition, where we thought of counting, well, a particular combination relative, so we take the fraction relative to the total number of times an event happens in this column. Okay, so now we talked about discrete random variables. Now let's take a closer look at continuous random variables. The definitions are very similar, and now we think of the probability of x, which can take on any value, falling in some small interval of size dx, is given by the probability of x times dx. And we call p of x, we call it a probability density. And whenever you deal with densities, you typically measure things happening on those densities via integration. For example, the probability of x taking a value in some interval is given by the integral from a to b of this probability of x times dx. Okay, maybe that's visualized better in this figure. So red in this case is a probability density function. And we want to know what is the probability of an x taken on a value in this infinitesimal volume element. Then we just integrate, or we sum over this green area that you see over here. And this gives me the probability of an event happening in that small range or small interval. And if we want to consider larger intervals, then we have to integrate this area. And that gives us the total probability of an event happening in that particular interval. So from A to B, for example. Okay, also for probability densities, we have this property that each probability should be larger or equal to 0. We have this normalization property. So the probability integrates from minus infinity to infinity. It should take on the value 1. And this makes sense, right? Because in this particular case, from minus infinity to infinity, I consider the possibility of x falling into this interval from minus infinity to infinity, and that of course always happens, so the probability should be 1. Okay, so finally something has to be said about a change of variables. So when we're dealing here with continuous variables, and we can apply a transformation to these variables to obtain a new description of this variable, which may be more convenient to work with. Consider, for example, the case that maybe your measurements are done in meters. Let's say meters, we're talking about distances, but I want to express this in terms of kilometers. Now, so you can apply this transformation, you multiply by a factor 1000, and that gives you the number of meters in a kilometer. But then also, so when we talk about probabilities in this continuous sense, we talk about intervals and these infinitesimal volume elements, dx. So in our original distribution, we have that, the probability of x falling into one, let's say, square meter or 1 meter is given by p of x times dx. Now I want to define my new distribution p of y in terms of kilometers, for example, but now my volume element is defined in terms of kilometers. So we have to apply some correction factor here. So this actually tells us that the new probability of y is given in terms of the original probability times some dx dy, where this second term is a correction factor for this scaling. I mean, we write absolute values here because the probabilities need to be positive. And in this case, we do not distinguish between reflections or changes of signs that take place in this change of variables. Okay, and if you take a closer look in this, if you're familiar with substitution of variables and integration, then you can derive that this factor is actually given by the differential of this mapping to y and the absolute of it. So actually this correction term can be dependent on the parameter y. In the case of linear transformation, it isn't, it's just a constant, a correction constant. But in general, it doesn't have to be, and then you can get very complex distributions, which no longer look like your original distribution. Okay, so those are some core things to take into account when working with continuous random variables. For continuous random variables, we can also define a thing called a cumulative distribution function. And a cumulative distribution function is defined as, so we write a capital P of x as the probability of x taken on a value smaller than this reference x. Right? So now we consider an interval from minus infinity to x. And we know that, we can write this as the integral from minus infinity to x of this probability x dx. I write these tildes there because these x tildes are dummy or integration variables. Okay, now these cumulative distribution functions, they can be useful to work with, and they have a very useful property, namely that if I again take this, the differential of this p of x dx, I obtain my original probability density. Okay, so that's all there is to say for now. Okay, so now let's summarize what we encountered so far. So in the discrete setting, we have this additivity property, meaning that if you want to know the probability of x taking on any of the values in some subset A, this is given by the sum of the probabilities of each x happening. So we have this additivity property. In the continuous setting, we also have something like that. And when we consider x taking on any value on the interval from a to b, this is given by the integral from a to b of these probabilities. Right? So we sum or we integrate all these probabilities. In both settings, we have this positivity criterion that each probability is 0 or larger than 0. Then we have this normalization thing. So if you consider the probabilities over all my set, over all my domain, then this entire probability should integrate to 1. And we have a similar thing in the discrete setting, meaning that if I sum over all values x of this probability x, then this should sum to 1. Then we have this sum rule, which refers to the marginalization, so sort of getting rid of one of the variables. So it's dealing with a joint probability distribution. And if I have such a joint probability distribution and I only interested in the x variable, I can sum over all these y components. And a similar rule we have in the continuous setting, where if I want to know the probability distribution p of x, given my joint probability distribution, it is given by the integral over given by my integral over the entire y of this joint distribution x and y dy. And finally, we also derived a product rule from these basic definitions of probabilities, stating that I can always recover my joint probability distribution by taking the product of a conditional distribution x given y times a probability of y happening independent of x. Okay, so now we have all the ingredients in place to derive Bayes' theorem, and this is an important identity that is useful for manipulating probabilities. So let's just first derive it, and then I'll give a bit more interpretation to it. First of all, we start off with the product rule. So we derived it, and so now we're going to use it. Then we take a look at the symmetry property, which basically says that the probability of an event x and y happening at the same time is the same as the probability of y and x. So we change the order here, happening at the same time. So of course we have the symmetry here. Now if we apply the product rule to this thing, then p of y and x is given by the probability of y given x times the probability of x. Now what we can do, we can equate both right-hand sides, and this gives me the so-called Bayes rule. So now I'm going to take a look, what is the probability, the conditional of y given x? It is given by the conditional probability of x given y times py divided by p of x. Okay, so now that we know the product rule and the symmetry property, it's pretty straightforward to actually derive Bayes' theorem, but it has some very important implications. It provides a way of changing viewpoints on probabilities. So on the left-hand side, we're considering a probability of y given x, and the right-hand side, a co-component is this probability of x given y. And this Bayes rule provides a way to sort of change your viewpoint on whatever problem you're dealing with. Finally, there's something to be said about this denominator, p of x. So I'm going to make a derivation, and then we'll give some interpretation on what we're looking at here. So first of all, we are dealing with a probability, a conditional probability here on the left-hand side with respect to the random variable y. And this means it's a probability, so it means that we have this normalization property, meaning that if I sum over all my probabilities y given x, then this sum reduces to 1. Let me just move it over there. Okay, The same holds for the right hand side then, right? Because we have this equation over here. So also if I take the sum over y in the right hand side, and then 1 over px, this p of x doesn't depend on y, so I can move it up front. This sum x conditional on y times the prior of y equals to 1. And okay, and from this we can directly derive that p of x can also be written in terms of the sum. Okay, so what we did here is we rewrote this denominator term, so this p of x, entirely in terms of the items that we see in the numerator. And we sum here over y, which is sort of, so we can think of this as a normalization constant that makes sure that this conditional probability indeed satisfies this property. Well, it's a given in most cases, but sometimes you do not have this p of x given and you want to derive it yourself. And then this identity plays an important role. Okay, so that's Bayes' theorem. Now, when we work with Bayes' theorem, we often give names to each of these individual terms. And what we're working towards through is finding a probability distribution of a conditional of y given some observation x. So we're talking about observations and then assigning probabilities to, well, to my other remaining random variable y. And in this context, we are dealing with a prior probability of y. So I was already calling it a prior, and we call it a prior probability because before I observe it, before I know anything, I have some prior assumption of y taking on some value. So prior says before observing x, I already have some probability of y taking on some value. And then I have a so-called posterior probability. So this is actually what we're after. So once we have observed an x value, we then take a look at what is the probability of y taking place. So this is, sorry. So this is after observing x. Then we have this other term, which also has a unique name, and this is called the likelihood of x given a particular y. And often this thing is referred to as a likelihood function rather than a likelihood probability distribution. And it has to do with the fact that we're dealing here with a conditional probability distribution, but it's a probability with respect to the random variable x. So it's a conditional probability with respect to x. But in this particular case, most often we're interested in this y variable. And in this formula, in this conditional probability, y acts as a condition. It's let's say a parameter that parameterizes this distribution of x. So if we look at the likelihood, it is a function with respect to y. And this becomes clearer later on, but it's important to realize this because sometimes you think, okay, why is this called a likelihood function and not a probability? When we talk about the likelihood function, we are probably interpreting this thing with respect to its conditional argument. And and this doesn't mean that if I look at all values over y, that this particular thing integrates to 1. Okay, so that's what we call the likelihood of x given y. And then finally here, let's use this color, we have the probability of x, and this is called the evidence for x. Okay, so that wraps it up for this video. In the next video, we'll take a look at some example and gain some more intuition of what these 4 individual terms actually mean.